Alright, so I wanted to make this video. Sorry we didn't use the Whiteboard, but snow day. And it's basically go over two examples of how you can find the electric field when you have a distribution of charge. That means instead of a charge that's located at a specific point, it's smeared over either a line, a volume, or an area. So in this picture, we can see the three basic ways that charge can be distributed. You can have a line distribution, and so we typically use lambda to represent the charge per unit length, or dq over dl, where this would be the little length of the line that I take, and dq would represent the amount of charge that was enclosed in that. Second, if we have an area, so a two-dimensional distribution of charge, that sigma is charge per unit area, or if you take a little area like we have right here, you would then enclose a charge equal to dq. Finally, we have a volume density of charge, where rho is the charge over volume, or again, if we take a small element of the volume, we would end up with a little bit dq of the charge. So these expressions allow us to write the charge from when we take a little segment, because with a charge distribution, you're going to have to do an integration. And so if you have a line of charge, dq would be equal to the charge per unit length lambda times dl. If you have an area distribution, it would be sigma times dA. And if you have a volume distribution, it would be rho dV. Now, the way that we use these expressions is you basically say, okay, I know the expression for the point charge, or the electric field due to a point charge, is equal to K, which is 1 over 4 pi epsilon naught as well, and then Q over R squared. Now what changes, and you can also see here in this expression, because it has the summation sign, that basically means if we're looking at the electric field at a point P, we would sum up all the contributions from all the individual charges, and that's what that summation sign is about. Now, when we're doing the distribution of charges like the line, the surface, or the volume, we're also doing a summation, but now it's an integration instead of a summation. And instead of q sub I, we're talking about the dq that goes in the top, like that would go in this place instead. And then we have to figure out how to integrate that. So you can see that all my expressions for dq have been placed in these different expressions for electric field, depending on what kind of charge distribution you have. Now the final thing that we have to worry about, because there's kind of a lot of details, is that as we're calculating the total electric field, we have to keep in mind that it's a vector. So for example, in this picture right here, we notice that in this sheet of charge, if we took a little element of area over here, the dA1, it would create this electric field E1 that points up and to the right. But if we go over here and look at this area, dA2, we have the E2 that it produces. Now those two together are going to give a net field up. And often when we're doing this integration, before we go through the mechanics of really integrating the expression, we can simplify the expression, because we have to think about, when I go through the entire shape, depending on what the charge distribution is, I'm going to get a lot of little contributions to the electric field, but I have to think about how they add up. So for example, in this picture here, the horizontal components of those two electric fields will cancel out, and then just add up, and you'll only have an electric field in the vertical direction. All right? So let's see that in practice, and I'm going to do two different examples. Now here is a segment of charge. And so in general, the electric field would be equal to K lambda times, now because the line of charge is along the x-axis, the length I'm going to call dx instead of dl. And the distance from this charge right here to the point P that I'm interested in is this radius right here. But I'm going to write that using the Pythagorean theorem. It's going to be x squared plus z squared, and it would be the square root of that, but then you square that distance. So remember that this represents r squared right here. Now, also, I have this unit vector r hat. Now, this is kind of similar to that example that we just looked at with the area, where the two components of the electric field would cancel out. If, as we go from this end of the line segment to this end of the line segment, our electric field is going to, on the left-hand side, is going to be kind of pointing to the right and up, and as we get to the middle and go over to the right, that electric field is going to be pointing to the left and up. So the net electric field for this picture is going to be upwards. So it's going to be in the z direction. So I need to figure out, like, how do I just look at the z component of the electric field? Well, I can use that angle theta, and what I know is my trig. It would be given by E times the cosine of theta, and so it would be this k lambda dx over x squared plus z squared, and then times the cosine of theta. Now, I'm going to have to integrate this eventually. Now, the dx tells me I'm going to integrate over x, but if you think about it, when I'm looking at pieces of charge over here, as I move along the length of the line segment, the angle that the electric field that it produces is going to change, the angle that it makes with the vertical axis. So the cosine of theta is not a constant term, but I want to write it in terms of my x and z and other variables that I'm working with. Because in order to do my integration, everything has to be in terms of just one variable. If I look at over here, the cosine of theta could be written as z over r, or z over the square root of x squared plus z squared. So I'm going to use that to rewrite this expression. And then we're finally, excuse me, going to have k lambda z dx over x squared plus z squared to the 3/2. And that's my integral. Now, it might initially be troubling because you might think z, well, z seems like a variable too. But in this context, z just represents the distance from the line of charge to where you want to find it. So z is actually like a constant number in this particular problem. Now, then we're almost ready for the integration. We would probably go from minus L over 2 to L over 2. But we're going to take advantage of the symmetry of the problem and the fact that each half of the line segment is going to contribute equally. So we're going to just multiply it by 2, and we're going to just integrate from 0 to L over 2. Now, we're left with this integral to do, which is, it's not all that great. It's an integral that you could do through trig substitution. And so you could look that up. Google's your friend. Guaranteed, if you look it up, you could find a YouTube video that would tell you that this integral, if you did it, would be equal to x over z squared times 1 over the square root of x squared plus z squared. So we're going to just say that that part we've completed successfully, and we're going to go and sort of put everything together. Oops. All right, and so I've done a couple steps here, so let's just talk about it. So I found what this integral was. I found that if we did that integration, I would get this expression. And so then I multiplied it by my constants out front, and then I got this expression right here, which I have to evaluate at my limits, which I'm allowing x to go from 0 to L over 2. And we have a couple things that are going to simplify. I had a z on the top here and a z squared on the bottom, so I'm just left with a z squared. And then when I evaluate the x at L over 2, that gives me this L over 2. But then that's how I'm going to get rid of the 2 out front. And then I have z times the square root of z squared plus L squared over 4. What is this telling me? So this is the expression that I got when I did all that work. What was I trying to find? I was trying to find the total electric field due to a segment of a wire that had a charge distributed over its length. I did change and said that lambda times the entire length would be equal to the entire charge of the line segment, and that's fine. There's nothing wrong with doing that. And so this would be an expression we could use. If we knew how long our segment was, if you're given a problem, you know how long it is, you can put that in for L. And I know how far away from the line segment I want to know the charge. That's Z. And then if I know the total charge, I put it in. Or if I know lambda and L, I can use that expression. So either one of these expressions can be used for a line segment. So you might be asking yourself, am I going to have to do this integration, on a test? It's always the question. And the answer is no. But I do want you to see the steps that are going through to get to this answer, because I think those steps are actually pretty important to just kind of understand how we see that the x components of the electric field cancel out, and how do we work through each step of this problem. It turns out that not too often do we have to work with a line segment. So I'm just going to write down the expression that we got just in the previous slide. So the line segment electric field was given as K lambda L over Z times the square root of Z squared plus L squared over 4. Now, the thing that is a lot more useful to us is answering the question, what would I do if the wire segment was really long? That is sort of asking the question, what if L was infinity? So I want to look at this electric field when the limit as L goes to infinity, which at first seems like a really bad idea, but we can simplify this. It seems like a bad idea because I have an L on the top and then I'm just going to get infinity, but I'm going to factor out the L in the bottom. Because if I do that, then these two L's cancel out, and so now I don't have to worry about that. And then if this L goes to infinity, that whole term is going to go to 0, and I'm going to be left with k lambda over z, and then 1/2. That's the square root of 1/4, which is the only term that's left under the radical, which just ends up to be 2k lambda over z. And so remember, z represents the distance from the wire, and this becomes an expression that we're going to use a lot. The electric field, due to just a long wire, is actually relatively simple. And so that's an expression that's kind of useful to us. Now, the other example I wanted to look at was just a little fancier. It's still a charge per unit length, so we're talking about lambda is the charge per unit length, or dq over dl. So when we're trying to find the electric field, we're doing k dq over r squared, and we're doing that integration. So again, I want you to kind of see that where we start is an expression that looks a whole lot like the electric field due to a point charge, except we're replacing it with a dq. Now again, here, there's a couple things to pay attention to. The ring of charge is in the xy plane, which really would be coming out of the page at you, and the z-axis is, of course, vertical on the page. We want to know the electric field at a point that goes through the center of that ring and some distance above the ring itself. That distance we're going to call z. Now, the amount of charge, we're going to take a little piece. It's a little piece of a circle. And if you remember, the arc length of a circle is equal to r times theta. So the little piece of the circle is r times d theta. And so here we use capital R for the radius. And so where this is k, and then it would be lambda times ds over r squared, and then k, it'd be lambda r d theta. Now let's take a look at what r squared is. In my integral, it's this hypotenuse here I called little r, which in this picture it's labeled. We can again use the Pythagorean theorem, and it's going to be equal to the square root of r squared plus z squared. Big R squared being the radius of the circle, of course. Now, again, we have some different components of the electric field. As I go around the circle, I'm actually going to form a cone of electric fields that as I go to all the different sides. But in the end, the only electric field that's going to persist is going to be the electric field along the z-axis. So again, think about as I go around, I'm going to make all my electric fields are going to form trace out a cone in space, but every electric field that's in one orientation is going to be canceled out by one on the other side. So there aren't going to be any x and y components of our electric field Again, it's only going to be the z component, which is going to be given by k lambda r d theta over the r squared plus z squared, and then times the cosine of this phi. Now the cosine of the phi, now that we're kind of used to doing this, we can write as z over, sorry, I want to just include z over the square root of r squared plus z squared. And so we end up with k lambda r times z over d theta times r squared plus z squared to the 3/2, because you have the 1 and then the 1/2. The thing that's kind of funny about this one is that the only thing that is actually a variable in this expression, which you might not have expected, is the theta. Because z is actually a constant, and of course the radius of the circle is constant. And so we're going to get 2 pi times k lambda r times z, and then r squared plus z squared to the 3/2. Now, the 2 pi came when I integrated the d theta around the entire circle. So what is the angle around the whole circle is 2 pi. Now, because the total distance around the circle is 2 pi r, and that would be the total charge, you can see we have a 2 pi r here times a lambda, so that could be written as kqz, because the q is the 2 pi times the r and times the lambda. And that's why those disappeared. And then r squared plus z squared to the 3/2. This is the electric field that's caused by the ring of charge if we're along the axis of the ring, but some distance above it, z. And notice what would happen if I went to the very middle, if I let z equal 0, and that's if I was right at the very center of the circle. Notice I would get 0, which kind of makes sense because all the electric fields on all portions of that ring would end up canceling each other out when you went the whole way around. So here are two examples of using integration to find the electric field for when you have a charge distribution.